Hi everyone. So for our project, we decided to explore the flow simulation and the CFD package within the professional version of Solidworks. So for this project, we decided to use our Lab 8 Cybertruck for the simulation. We wanted to basically determine the coefficient of lift and coefficient of drag, hopefully for this vehicle, and kind of compare those to real values presented for different vehicles and what Tesla says based on our model. Our model is made from photos, so we took a rectangular block and basically posted the pictures on each side. Made sure the block was the general size of the Cybertruck as posted on their website, and then basically cut it out. So it's pretty close, but obviously like the wheels and the underside of the vehicle is not fully defined, or modeled. So we're gonna get a little bit of change, but we also just kind of want to see what we could get out of it. So to access the flow simulation, if you don't already have it, you're gonna want to have to go in add-ins and go SolidWorks flow simulation. Check that box, and it should pull it up. And this will give you two ways to access it, but the easiest is going to be flow simulation. Once you click on this tab, you're giving a lot of these options. You can actually click through new and set up a project that way, but we found that the wizard's kind of the easiest way. And obviously, like all this stuff you won't have yet. This is our old simulation. But we can go ahead and give it a name. Call it the class presentation, configuration current. So we're in the file with the Cybertruck. It's going to use this project, this assembly file to do the simulation, and go ahead and leave that. So basically we wanted to put everything in USA so it's a little bit easier to understand and kind of give us values that we're a little bit more comfortable with and have used a little bit more in our life. So basically we're going to use those, and then this will give us everything in like velocity in feet per second. You want to make sure you get units right there, and temperature, Fahrenheit. So we'll go ahead and hit next. And this will give you two options. So for your analysis type, you have internal flow or external flow. Internal flow you're going to want to use if you have a pipe or any kind of internal flow. But for our application, we're going to use external because we're going to see how the air flows around this vehicle and eventually get the coefficient of lift and drag from that. We decided not to consider these closed cavities or anything because we didn't really need to include that, but we did decide to select gravity. And this is kind of one of the first places you want to really check your model. So looking at kind of our coordinate system down here in the bottom left, we can see that gravity should theoretically be acting in the negative y. And currently it's set up for the negative z, so we're going to have to go ahead and change that. We'll just copy this value over, zero that out, and put that in. Alright, so we're all set up here. We're not going to have any rotation or free surface, time independent, radiation, none of that, so we'll hit next. And this is basically where you select your fluids. So you have options, you have all these gases. You can set liquids, steam, real gases, compressible fluids. But for ours, we're just going to do air. You can either double click or click that and hit add. This will pull in our fluid, and it gives you a couple more options based on what fluid you have. And we're going to leave this flow type as laminar and turbulent and leave humidity unchecked. If you want to include humidity, you would select that and it will give you that. But we're going to leave it unchecked. Go ahead and hit next. These are basically your wall conditions. We left these all the same, adiabatic wall and no roughness. We're not considering that. And then basically you're going to want to make sure you fully understand kind of these values that's automatically putting in for you. So the pressure, it's at 1 atmosphere and standard temperature, so 68.09 degrees Fahrenheit. That all checks out. And right here again we have something we're going to want to input. So looking at our model, we want the air to pass through the front of the vehicle and around it, so we want the air to be acting in the negative z direction. And for this we tested the vehicle at 65 miles per hour, and so that's going to be roughly in feet per second of a negative 95.333 repeated feet per second. So we can go ahead and hit finish on this. This is going to set up basically everything we've given it, and then give us a few more options. So over here on the left, you can see this should be your project your study you're looking at currently. We have some of the old ones right here. And we're going to go ahead and select this computational domain. So right here, you get a box. This is basically what it's going to solve for, and you'll be able to put the error in through the system and through this box. And you can either slide these little sliders for each section, or you can input the values in here. Basically, what we did is we brought these in as much as we could so that there was still space around the vehicle. We wanted the air to pass around the vehicle and not be restricted or blocked by this wall. So we have enough space for it to those flow velocities to change from the vehicle. We can observe those. So we'll bring this one down and we'll grab, not to hit that box, this view, and bring this all the way up as if it was the floor, because we want to see how the air interacts with these wheels, but we don't want air to pass underneath them. So we're just basically gonna bring this as much as up as possible at the base of those tires. It's gonna fight you a little bit. We got a lot closer earlier, but I'm just gonna leave it at that. Leave a little bit of space at the front for that profile. A little bit of space at the top. I'm actually going to make this a little bit bigger, and some space behind so you can see how the flow straightens out and check all that later. So we'll leave this as 3D simulation. You can do 2D simulation, but this is perfect for us. So hit the check on that. Here you can select your fluid domains and subdomains, so you can actually in here pull up this box. It will let you adjust the fluid that you selected earlier. And then set up boundary conditions if you want to set up any of that. But basically, we're going to move right into here, and we're going to right-click on goals and insert goals. So for this project, we had a couple goals that we wanted. Initially, we just wanted to include a velocity, an average, and a max. We don't need a min, because that's probably just going to be 0 somewhere. And so we'll have those selected. Those are just basically general values we wanted to find. But they're not needed for this coefficient of lift and coefficient of drag simulation. And then here we look at our coordinate system. Our drag, we're going to need the z, and for our lift, we're going to need y. We'll select those, and then go ahead and hit the check mark. You have actually a lot more options if you want to explore those, but we're just going to go ahead and roll with these. Again, right-click up here on those goals, and now we're going to insert the equations for the coefficient of lift and coefficient of drag. So we can go ahead and give this a name. We'll do CL for coefficient of lift, and I'll pull up these equations from our report. So here's the equations we have. We have the coefficient of lift. We have a lift. This is going to be outputted in pounds force. So we have a gravity in there. We have a 1/2 density velocity squared times area. And then basically the same thing with drag. The only tricky thing is this area. The area, there's basically two ways to think about it for the coefficient of lift and coefficient of drag. Basically the one we selected was a sectional reference area, basically perpendicular to the flow. So to get those areas, we actually had to pull this project into a different window, project basically a sketch of this outline onto a wall, and then you can measure the area of that. We'll put a screenshot of that and how we kind of had that set up. So that got this whole area, and then basically in here I have the equation already copied over. I'm just going to paste it and explain it. So we have our GG force Y, which is this force right here. This is going to be our lift force. And then we have our gravity. And then we have our 1/2 density velocity squared times the area. So we have all this inputted. We have no units because it's going to be a coefficient. So we can go ahead and hit the check mark. And then we're going to go back up to the goals, insert equation goal, and insert the coefficient of drag. So again, copying this over. and go ahead and hit green check mark. So once we have all this, we have basically everything we need. The mesh, you can set this up yourself, or you can hit run. Run will set up the model and it will mesh over it for you. And basically that's all we need for this project. When you have this window up, you want to make sure, especially if you've done other calculations or solved for anything, that you are conscious of these options up here. Basically, if you've already done one, it will have the mesh deselected and the continue calculation. And if you change some things and you messed up your first one, you're going to want to click mesh, click solve. It will do a new calculation, and so you're fixing what your mistake was. If you don't, it will either give you an error, or it's going to compound something that you don't need. We're going to leave this at run at this computer and use all cores, and go ahead and hit this run. So this should pull up a window outside of SolidWorks, and you should see it pull up on your taskbar. There we go, and open this up, and this is basically going to prepare the model, and you should get a slider. We'll check back once this is done, but basically we're just making sure that everything's solved out.
Okay, so here we can see our progress bar. We can now see that all of them have been completely achieved at 100%. We can see down here that our calculation is done, that it ran an iteration of 57 times. And this is the current value at that last iteration, and then it also has an averaged value over all the iterations for us. So we know that our goals are complete, and we can go ahead and exit out of there. Now we can move into our post-processing and determining of our results. We can actually create several things. We can create goal plots, XY plots, surface plots, cut plots, long list of options. Something that we want to do actually is to create some goal plots first. So we're going to insert. There we want to grab our goals that we had already decided before. For us, we can actually grab all of them and see all of the values there. We can actually not only show these in SolidWorks, but we can also export the file to Excel as well. So if we go ahead and click show, we can see down here that these are all our values that were ran. Again, these are average velocity, maximum velocity, our force on our Y, force on our Z, our coefficient of lift, and our coefficient of drag. Units along with those, a value of the last iteration, our average values, min, max values, progress, and our convergence. So another thing we also are noticing down here is our convergence. We want to make sure that everything converges. That way we make sure that our solution is accurate and not constantly changing, and we don't have great outliers in our data. And that will also show with our progress at 100% there as well. So there we can click out, and we've got everything that we want. Again, we can export that to Excel, where we can then create a bunch of other plots and graphs with that data if we so choose. So now we can insert flow trajectories. We'll right-click Insert. So what we want to do is we want to find the plane that is perpendicular to our flow. So we know that flow is in our Z direction, and for us the front plane is perpendicular to that. So then we can go ahead and select that plane. Now we want to put it close to our domain layer. If we just pick a large value and roll with it, it'll actually put us cap out and put us on that domain boundary. Because it's an inlet boundary, we can't leave it exactly on it, so we're going to bring it in just slightly. So for us, 14.5 will work just fine. Now we can select the number of points that we want to solve at. If we click, just put that as a large value, again, 1,000. You can tweak that for your solution as you go and come back and change it. Now we can go down to our arrows. We'll leave it under dynamic trajectories. We'll leave it under arrows. Our size of our arrow we'll actually leave as 10. And then we can change the distance between the arrows. We can actually drop that down. Let's just say 15. We can also select different variables that we want to solve for. For us, we're going to choose velocity. Now we're going to solve. We'll Okay, so there we go. We've got a flow trajectory velocity plot. We can see all of the flows happening in and around the vehicle. If we can zoom in and get our flow that's happening, that's getting pushed down around the vehicle and up above the vehicle as well. You can see that especially underneath the truck. So from there, we have that plot. We can also introduce other plots. So we can go ahead and hide that. We can introduce a cut plot. Cut plot will show us halfway through our surface or our part. So we can go ahead and insert. So for us, we don't want to analyze the front plane, but really want to analyze the side view. So for us, that is the right plane. Like that, we'll leave our distance at 0 for the center. Now, a couple of things we can play. We can actually do contour, isoline, vector lines, streamlines, and we can show our mesh. And you can actually select multiple of these at a time. For us, we found that contours and streamlines actually seem to look the best. So again, we want to use velocity. We can select different ones, including pressure, which might be a good one too. Velocity, we can set this at our number of levels. We can select this drag bar. For us, we're going to peak it out just so we can see everything. And then again, our velocity, and then our different scale lengths that we can do. We don't really need to mess with that. It should automatically adjust for us. But you can go in and refine that better if you so choose. So from there, we can go ahead and hit OK. And so that will give us a nice plot of what the velocity is doing in and around our car at the middle of the truck. So that way we can see it a lot better. We can see where we're getting our flow trajectories in and around the nose. And then we can also see our concentrations in and around the bed area. And towards the back, we can see our vortex eddy forming in our box area, as well as behind the trailing edge of the vehicle as well. So those are all very important points to see during our analysis. Okay, we can also insert other cut plots. We'll go ahead and hide this one, create a new one, insert. For this one, let's do contours, and we'll leave it at that, and we'll do pressure instead. So that way we can see our pressure concentrations. We can go ahead and put ISO lines on the top of that as well. Again, we'll max the slider bar out for our number of points. But again, we also want to select our right plane, so that's what we're evaluating on. From there, we can go ahead and hit create. And so now we can see where we're getting our pressure concentrations in the flow. So as we can see, we would expect a high pressure concentration in the nose area. And for that view, that's pretty much about it for large pressure concentration. But we could, again, change that and slide that out to say where our wheels are and get values there as well. So again, very helpful, useful points in analyzing our aerodynamics of the Cybertruck.
Okay, so now that we've shown you how to set up the problem and shown you how we can do some post-processing to look at the results, I'm going to kind of talk about our actual results. So if we go to our goal plot here, we edit our definition, we can actually export all of the data that we've tried to be looking at. We can export it to Excel so we can see it a little better. So when you export this to Excel, you get a few different pages. This first one's just kind of a summary of all the data, all the goals that you set for the simulation. So here we show the average velocity, the maximum velocity, the force in the Y and the Z. And then these two lines here, the CL and CD, these are calculated coefficients that we used those equations for. So in these pages down here, it'll actually show you the graph of the different goals based on the number of iterations. So here's the coefficient of drag for over a set amount of iterations. You can see initially it's a really rough calculation and it starts to refine as it keeps going. And that does the same thing for all of the goals that we set in our simulation. And then here, this last page will show you the actual raw data in case you want to do some data processing on your own. Okay, so in our simulation for our report, like I said, we had a much more refined, accurate answer. So we made the domain a lot bigger to make sure the air at the edges of the domain weren't interfering with the car at all. And what that showed was a coefficient of drag of about 0.69. So I'm going to show you this simulation here. These people also attempted to simulate the coefficient of drag of the Tesla Cybertruck. So they pitted it against a few different other production trucks, the Dodge Ram, the Ford Raptor, and then of course the Tesla Cybertruck. So their findings show that at this 60 mile an hour around speed, the Dodge Ram had a coefficient of drag of 0.59 and the Ford Raptor had a coefficient of drag of 0.56, which is really close, or a lot closer to our results. Now their results did show that the Cybertruck had a coefficient of drag of about 0.39. There's quite a few reasons for this. Like we discussed earlier, the bottom of our model isn't, there's no data there. It's just flat across the bottom. The wheels that they have modeled here are, there's no holes through them, so the air is just going to flow around them. And then they've modeled it here with the bed cover closed. So ours, there's an opening here, of course, and in the graphs you can see the air flowed down into the bed and slow down quite drastically, and obviously that's going to cause a lot of drag. On Wikipedia here, they've got a whole page dedicated to the coefficient of drag for production vehicles. So you can see here vehicles like the Hummer H2, the Land Rover Defender, a G-Wagon. Those all have coefficients of drag in the 0.5, high 0.5 range. They list a typical truck as 0.6, so fairly close to what ours are going to be. Like I said, our model not having this bed cover here is going to cause a lot of drag and is probably going to be the biggest reason why our model is up in this range. Okay, so right around the time that the Cybertruck got announced, Elon Musk responded to one of these other investigations. This group here did a simulation on the Cybertruck. You can see their model's pretty rough. This was definitely right around the time that the truck was announced, but Elon kind of boasted that the Cybertruck could hit a drag coefficient of about 0.3. What this probably means is that they would have to redesign the wheels so that they're as aerodynamic as possible. There would be no holes in the face of the wheel. They'd probably have to lower the Cybertruck. There would definitely be the bed cover. There probably wouldn't be any fender flares. And they'd probably have to change the surface of the Cybertruck. So the Cybertruck that we modeled and that other groups have modeled is just bare stainless steel, like it was announced to be. To get that more aerodynamic, you'd have to paint it and clear coat it and then put some sort of a wax on top of it to try to make it as smooth as possible. Okay, so with the way that we set up this simulation, the truck is actually facing the positive direction. So we had to input the flow in Solidworks in the negative direction. So when we did that, the velocity was in the negative direction. So the force that's calculated on the truck is going to be negative. And so with the way that we set up our equation, we left out the absolute value around the coefficient of drag. And so what that's going to do is it's going to also give us a negative coefficient of drag. That's just because of the way the model was put into the simulation, the direction it's facing, and the way that we had to set up the flow. Okay, so as you've seen, in just a short while, you can take a part that you've been designing in SolidWorks and throw it into a flow simulation and see how it interacts with a fluid. SolidWorks is really great at this with a lot of its different packages, being able to just quickly take a part that you've been designing, put it into some sort of a simulation, and then see its results. Obviously, SolidWorks isn't going to be the most accurate toolbox out there. There's a lot more that are going to be more precise and going to be able to give you a lot more ability to change different characteristics of the simulation. That might include like Star CCM. That program lets you change a lot more that SolidWorks just doesn't have settings for. But what this toolbox does let you do is it takes a part that you've been designing, quickly just do a fast simulation to see how it interacts. This could be really useful if you're designing like pipes. You can just throw it into this program real fast, see how fluid flows through it, and then change your design roughly based on those results. Thank you for watching this video. I hope this has been helpful and hope it teaches you guys how to use the flow simulation in SolidWorks.